Hello and welcome. So today we're basically becoming atomic detectives. Yeah, we're going to go on a journey deep inside these tiny grains of dust that have traveled across the galaxy for billions of years, all to figure out the secrets of long dead stars. So let's just dive right in, starting with a question.
Just think about that for a second. I'm not talking about something from the early solar system. I mean matter that existed before our sun was even a thing. Can you imagine the stories it could tell, the secrets it would hold? Well, guess what? It's not science fiction. Scientists are actually doing this. Tucked away inside meteorites that fall to Earth are these microscopic time capsules from the ancient universe, and we're getting really, really good at reading what's inside them.
Okay, so what they're looking for are these things called pre-solar grains. And the name, it pretty much tells you everything you need to know. These are tiny specks of literal stardust that formed in the atmospheres of stars that lived and died way before our solar system even existed. Now, these aren't just any old dust particles. They're these microscopic bits of a special kind of carbon that was forged in the fiery atmospheres of stars, specifically red giants. This stardust then just drifted through space for who knows how long before it got swept up in the cosmic cloud that eventually became our sun and all the planets. So, to really wrap their heads around this ancient stardust, scientists did something pretty clever. They decided to compare it to a modern version they cooked up themselves, right here on Earth. This sets up a kind of cosmic bake-off, if you will. So on one side, you've got the pre-solar carbon, the actual stardust. It came from a red giant star, cooling down nice and slow as it floated out into space. And on the other side, we've got the homegrown stuff, made in a lab oven and cooled down super fast. We're talking like 10 milliseconds fast. And this right here is the big question. I mean, on the surface, it's all carbon, right? But does that journey, the way it was born, actually change its fundamental structure way down at the atomic level? This is the mystery they set out to solve. Now, to see a difference like this, you can't just pull out a regular microscope. You have to go way, way deeper, down to the level of individual atoms. And to do that, you need a special kind of tool, something that can create a blueprint of the atoms themselves. The whole process is kind of like taking an atomic fingerprint. Scientists fire a beam of electrons at one of these tiny carbon grains. As those electrons bounce off the atoms inside, they create this unique scatter pattern. If the atomic structure is really orderly, you get a sharp pattern. If it's a mess, you get a fuzzy one. But it's not just about looking at a cool pattern. They use this powerful math tool, it's called the Debye scattering equation, to turn that visual pattern into hard data. This lets them put an actual number on just how orderly those atoms are. And that brings us to the key clue in our whole detective story, a measurement called crystallinity. This is the number that's going to reveal the real difference between our two types of carbon. Think about it like this. If you just dump a pile of bricks on the ground that has super low crystallinity, it's just a chaotic mess. But a carefully built brick wall that has very high crystallinity. The bricks are arranged in a neat, repeating, and really stable pattern. So, which carbon is the brick wall, and which one is the messy pile? Okay, so here's the first number they got. 40%. Let's just let that sink in for a moment. That 40%, that's the score for the ancient stardust. 40% of its atoms are arranged in that perfect, orderly, crystalline structure. That's actually a pretty neat and tidy arrangement for something born in the chaos of a star. All right, now get ready for the number from the lab-made version, 12%. Just 12%. I mean, that's a huge difference, right? The stardust is more than 3 times as orderly as the carbon that was made in a super-controlled lab environment. So why? Well, the answer turns out to be kind of beautiful in its simplicity. It's not about what it's made of, it's about how it was made. And the secret ingredient is something we can't really replicate in a lab, just time. I mean, just look at that gap. The results are so clear. 40% versus 12%. The atomic structure of that stardust is just way more organized. The atoms had the chance to find their perfect little spots to settle into that strong, stable, crystalline form. And here it is. This is the key phrase from the research that says it all. Time at temperature. That's the whole story, right there in 4 words. So it all comes down to this. The stardust, it cooled gently over these really long periods as it drifted away from its star. It had a ton of time at temperature. The atoms had all the time in the world to move around and lock into that highly ordered 40% crystalline state. The lab carbon? Nope.
It was flash-cooled in milliseconds, which basically froze the atoms in place in a much more chaotic, jumbled-up arrangement.
Okay, so this is a really cool cosmic detective story, but why does it matter? What can we learn from a speck of dust that actually helps us back here on Earth?
Well, for one thing, it gives us a direct physical model of how dying stars actually seed the galaxy with the building blocks for new planets and for life. But it also gives us a kind of blueprint. If we can understand the conditions that create this superordered carbon, we might be able to create new materials with amazing properties here. Imagine things like advanced filters or new kinds of protective coatings, all designed using a lesson from a long-dead star. It's literally a lesson from the cosmos that could build the technology of tomorrow.
It really makes you wonder, doesn't it? Billions of years of cosmic history, the whole story of a star's life and death, and even clues to future technology, all of that encoded in the atomic structure of a grain of dust that's smaller than a single cell. What else is just waiting out there to be discovered in the next meteorite that falls?